Module 11, we're going to be going through an edited version of Exploration 10.1 from the textbook. So the exploration starts off by giving you these two pictures. So we have some food on a plate on the left, and we have some food on the plate on the right, and it asks, are the food portions shown above the same size, or is one larger than the other? So this is, just really your opinion, but it is the case that a lot of people actually say that the one on the right looks like a smaller portion of food. So in fact, it's the case that they have the same amount of food and they just actually have a different plate size. This is actually known as the Delboff effect. I'm not really sure if that's how you say that name. Sorry. I'm saying the Delboff illusion. Might be pronouncing that wrong. You've probably seen articles, television reports about the growing obesity problem in the U.S. Many reasons are given for that problem, ranging from fast food to lack of exercise. One reason some people have given is simply that the size of our dinner plates has been increasing. It may be the case that people tend to put more food on large dinner plates without even realize that they're doing it. So to investigate that claim that dinner plates are getting larger, some researchers gathered data for American dinner plates being sold on eBay on March 30th, 2010. They recorded the size of the plate and the year of the manufacture of that plate for 75 different plates. So here we have some examples there. So 1950, they found a dinner plate with 10-inch diameter. 1956 made plate was 10.75-inch diameter, etc. So what would be the explanatory and the response variables, and are they categorical or quantitative? So in this case, the explanatory variable is the year that the plate was manufactured, and that would be quantitative because the year will be a number. The response variable here would be the diameter of the plate in inches, which is also quantitative because it's also a number. Question 3 asks us to explain what it would mean for there to be an association, a correlation between the explanatory and response variable in this study. If there was an association, it would mean that we would be able to use the year to give a bit of a prediction of the plate size that we expect to get. Because there would be an association correlation, we would expect to see some sort of pattern, whether we're suspecting that perhaps it would be an increasing pattern, meaning as the years get bigger, the plate sizes get bigger, but we don't know for sure if that's happened yet because we haven't explored it. Part 4 says to copy and paste the plate size data into the correlation regression applet. So I have that given here. I'm going to copy my data set as given. I'm opening up the Rossmann-Chance applet, clearing out the original data and pasting and hitting use data. Okay, there it is. So we see the explanatory variable is always along the x-axis. That's the year. The response variable is on the vertical axis. That's the size of the plate. Okay, so I have made a screenshot of our scatter plot. It asks which variable is on the x-axis and which is on the y-axis. So in the x-axis is the explanatory variable, the year of the manufacture of the plate. Y-axis is the response variable, the diameter of the plate in inches. Part 5 asked, is the direction between the explanatory and response variable positive or negative, and to write a complete sentence to explain the meaning of that being positive or negative. Okay, so looking at the scatter plot, it does look like it is increasing. So the direction is positive. Increasing data means the direction is positive. So what would that mean in context? In context, that tells us that as the years increase, the diameter of the plates is tending to increase. Number 6, does it seem reasonable that the form of association between the two variables is linear, or does it seem like there's strong evidence that it's not linear? Again, looking at the scatter plot, it seems reasonable to me that a linear function could be a good model for that data. A straight line through there seems reasonable. And then part 7, does that association seem strong, moderate, or weak? I would say that it's kind of in between moderate and strong, more towards a moderate sort of association. If you look at that scatter plot, it isn't like going to be a correlation coefficient of like 0.9, but it might be 0.7, which is kind of edging towards a moderate association. So part 8, does it appear there are any unusual observations? If so, describe that in context. So looking at this scatter plot, perhaps this data point down here in the bottom right might be a bit unusual. You notice that that is a plate that looks like it was made around maybe, well, actually, let's go look. If I click on that data point in the Rossmann Chance applet, in the bottom left, it says that that is the year 2004, and it was a plate that had diameter 10.13. You'll notice other plates that were made in 2004 tend to be kind of higher diameter up here. So that might be what I would consider an outlier. This one over here maybe is also an outlier. It looks like it was made in 1956, and it was unusually high diameter plate, 10.75 inches in diameter. So I said the plate made in 1956 with a diameter of 10.75 inches is an unusually big plate for that year, and the plate made in 2004 with a diameter of 10.13 inches is an unusually small plate for that year. So will the correlation coefficient be positive or will it be negative? Since we think the data is increasing, it will be positive. And approximately what value do I guess? Okay, this is my own guess. I am just going to guess 0.7. And now it's asking finally to use the applet to get the actual correlation coefficient. So the actual correlation coefficient, if I click the correlation coefficient button, it says it's 0.6. So my guess wasn't that far off. I said 0.7. Remember, the symbol we use is R because this comes from a sample. So our sample correlation coefficient is 0.6, which it's positive because the data is increasing. And it's kind of moderate correlation. It's not 0.9 and 0.85, which would be strong correlation. It's 0.6, which is moderate correlation. If we use the Add Remove Observations button and we enter a new plate into the data, we're going to enter a new plate into the data that has year 1950 and plate size 11.5. We're going to add that in, and we're going to see that it doesn't fit the overall pattern and describe what it does to the correlation coefficient. So 1950, 11.5. So down here in the Add Remove Observations, I'm going to go into the X value and add a year of 1950, and I'm going to put a Y value of 11.5 and hit Add. Okay, here it is. Here's that new data point, 1950, 11.5. See it right there? And now notice the correlation coefficient. The correlation coefficient changed to a value of about 0.37. The outlier data point of 1950, 11.5 changed our correlation coefficient to become 0.37. When we add an outlier, it made the data less associated with a linear function.